Okay. So let me. Okay. Thank you so much for August's nice introduction about my previous education and the work experience. So I'm happy to introduce our recent work for get the data and fine tuning. That's the fault the network to comprise. So this work over cooperation with Harris, Professor Taylor, and my supervisor Olga. And in this work, the uh, focus issue is more about model comparison. In recent 5 or 3 or a decade, people in machine learning community has witnessed great changes in deep models like Llama. Now we have Llama 3.2, VIT, and YOLO 30. I don't know, there is YOLO 30, very fancy. And people try to reduce model size by design some well-designed architectures, like let's say efficient night, mobile night, to fit them into edge devices. And we have some ResNet18 like models, which is now it sounds like old school, but it's powerful, but still tiny. But they are not tiny enough because nowadays the question is those models are powerful but oversized. And when you want to deploy your model to a real situation, for example, edge devices, you would need to consider how to compress a deep learning model to fit it into some smartphone like your iPhone, your Samsung phone. People say, okay, there are some classical solutions. For example, you have a filter of your favorite ResNet18 or some models. This is the full model. And you can do model pruning. You just find some less important neurons, let's say minus 0.6 or minus 0.9 or 2.8. The magnitude of them are very small. Just delete them or zero them out. Sounds good, but you still need fine tuning to recover performance. This is not good. And people say, okay, let's do quantization. It just replace this some float number with integer 8. Looks good. For example, replace minus 0.6 by 170. Looks easy, but you still need data to do collaboration to decide the data range. Or you want to do quantization over training, you say you need to do application again, which is time and resource consuming. And people also want to say, okay, why not knowledge distillation? You're going to train a small model that can imitate the behavior of the big model. But you are doing training again, man. So that's not good. You need data of fine tuning. In our work, we just open the well-trained model, for example, the ResNet18 trained on image night. If you look at the first convolutional layer of this ResNet18 trained on image night and plot them with some nice color mappings from some libraries, you might find something like this. There are some filters, you see, and they look very similar. It's kind of, I don't know, butterfly or blocks. Very nice. For example, this one close to this one, and this one is similar to this one. Yeah, these similar filters give you some kind of hints. If there are some redundancy, for example, if you plot or if you first do the calculation for the layer risk correlation by just doing the activation matching between each channel, and then assign each channel to its best matched channel using a greedy pairing algorithm according to the correlation matrix. You might find from the very beginning, first convolution layer to even last convolution layer, the correlation number distribution looks okay. At least most of them distributed at 40%, some or 0.4 here, which means there are some redundancy we can find by our eyes, both in the patterns or in the correlation map. The question is, if you do pruning, you are just going to delete one row or this row. It's not good. Why not fold or reuse the similar structures instead of zeroing them out? So our contribution is a data-free and fine-tuning-free model comparison methods. We call it model folding. So I have a very small animation showing the process of model folding, I need to restart again. There is 3 by 16 weights matrix. For example, this the weight of a linear layer of your model. You are going to cluster some similar patterns. For example, there are some neurons look similar. For example, they are both in red or in green or orange or blue. Yeah, sorry, I'm colorblind. Yeah, you know there are some similar groups. That's good. You are going to just do clustering, and then you merge them to have this merged C0. You see it's bigger because it is averaged, and we do it by formulating the model folding problem as a low-rank matrix decomposition problem. So the k-means clustering appear the optimal solution in this setting. You first try to find similar group channels, cluster them by k-means, and then you merge the channels. Easy? That sounds good. Then if you are going to apply this method, you might find from, for example, you are going to follow the ResNet18 trade on C14 from 0.3% sparsity, and you increase the sparsity to 100%. The text accuracy at some point drops suddenly. For example, here, 50% it goes down 20 or 30. This looks not good. Why? We investigate this phenomenon according to a paper called REPEL, Renormalizing Permuted Accuracy for Interpolation REPEL. In order to maintain accuracy, the data variance of the compressed and uncompressed model must be aligned. For example, in the right plots, the variance ratio must be close to 1. If you think about where we need this sample here, you're going to merge 2 channels in a group, in a cluster, channel A and channel B. You can merge the weights easily. Just WA plus WB divided by 2, that's all. But in terms of the batch normalization layers used in ResNet18, you have rolling in and rolling variance. Those data statistics need to be taken care. Because the sum of 2 random variables is not equal to the sum of variance of 2 random variables is not equal to the variance of the sum of 2 random variables. There is a covariance. So in the REPEL paper, you can just take the folded model, just run the spectrum layer on the original training data set or small site or calibration data set to get the correct bin layer statistic. So we use this one as the third step after merging. Now let's have a look at the performance. If you apply REPEL after clustering folding, this curve shows the performance of folding result after REPEL. You see, and 50%, 60% sparsity, 80% sparsity. The folded ResNet18 with REPEL can still give you good and high accuracy, like 80. Here we didn't use fine-tuning, which is good, but not good enough, because here we still need something like original training data set or small site of calibration data set. Oh, that's not good. So we need to avoid using it. So in our paper, we proposed 2 data-free versions of REPEL. One is for the AR, approximate REPEL, and the second one is for the DIR, deep inversion REPEL. In the left, Harris contributed a lot here to implement approximate REPEL. The basic idea is the following. If you can fold the convolution layers channel into a group, you can merge the bin layers into a cluster, the convolution layers together, and the bin layer statistic or the channels should also look similar. So we are just using the summary of the intra-cluster correlations and the scalar to control the scaling factor. Should we increase or decrease the weights? Okay. Here we do not need the data. just using it, just by doing merging the bin layers into its previous convolution layers and computer the intra-cluster correlation. Yep, easy. And in the fold DIR, basically, we need to solve some data from the well-trained model. We use a technique called deep inversion. You can run the application to solve the kind of semantic data, and you can run this model, a folding model on the semantic data to get the estimated running mean and running variance. They should be very close to the original data statistic. And then we also evaluate these two data-free versions of REPEL, the two lines and this line. So if you look at here, we compare the model folding with REPEL. Without REPEL, without REPEL is naive for the naive and approximate REPEL, AR, deep inversion REPEL, and FM. FM is a method called the iterative feature merging, which are also data-free structure pruning proposed in 1 or 2 years ago, accepted by ICLR 2024, I guess. But here, if you look at the high sparsity, 80%, this data-free REPELs can give you close performance as the fold with REPEL, very close, especially for the DIR. And for the variance, if you look at here, the variance is very close to 1. But for others, for the naive or the others, it looks like not be correct. Well, so now we can use this totally data-free REPEL compressed models. I'm going to show you some interesting results in the computer vision tasks. The first row, it shows ResNet18 performance. The second row is VGG11, which with normalization layers. And the first column is the model trained on CFR10. Second row is for more difficult task, ImageNet. And we already knew the model folding can defeat FM. And here we also compare the naive methods. SPL1 is the magnitude structured pruning L1 and magnitude structured pruning L2. You see, if you increase the sparsity, somehow here, well, 30% the structured pruning can easily fail. And 60% the FM will also fail, but folding with REPEL and data-free REPEL can both give you accuracy above 60%, and somehow for the folding DIR can give you like 85 or close to 90% accuracy. And even for some difficult task, ImageNet at a high sparsity, if we say 40 or 50 is or high, you see this for the REPEL and for the DIR and for the AR can stay like 20 or 10. And if you look at the VG11 without residual connection, VG11 is deep model but without residual, which means it's not the well designed. If you look at this architecture, and the FM will quickly fail at, I don't know, 1% sparsity or 2% sparsity, and the structured pruning will fail at 20 or 10. But if you look at here, well, even for some kind of stupid models, model folding can still give you good result here. Yep. And looks interesting. And additionally, we also investigate with different training regularization methods, what will happen? Because people are doing L1 regularization to force model and some sparsity here. And if you train a model with L1 regularization, the model itself will look like kind of sparse. So the model folding may not defeat it if you train model with L1 regularization. But the good thing is that the people publishing the models on the Hugging Face, and nowadays people are using L1 2 regularization, but for performance and the sparsity, the kind of sparsity. So in this case, model folding can defeat other solutions like structural pruning L1, structural pruning L2. Even if we apply folding on the apply repair on the structural pruning L1, L2. Yeah, you look at here, both here. Okay, and then people may ask, you are just planning some models with this well-designed one. What about if you increase the number of channels? Do the wider networks present more opportunities for the model folding? The answer is yes. So basically, you can increase the layer weight, and by doing this, you will increase the matched correlations because you will still have the same task. For example, in this naive model MLP, one linear layer plus Bn plus ReLU plus fully connected classifier and trained on CIFAR10. Very simple. If we increase the number of channels, the redundancy will be increased. Why? Because you definitely can train the model easily with some evaluation and learning rate. And if you do the folding here, for example, from 1 times wise and up to 4 times wise and 8 times wise, the performance you see can stay very, very high here, almost nothing loose. Also, for some little bit difficult task, CIFAR10, if you try deeper, more deeper model, much deeper model, ResNet 15, 50. And at here, if we look at here, yeah, much better than this one times wide model. So in this way, it shows the consistent performance gains if you increase the weights or number of channels or the number of number of channels or the neurons. Besides this, we also evaluate an interesting topic. We extend model folding to model merging. You can think about model folding kind of method to cluster n channels into, let's say, 75% n. But in this way, we're going to achieve sparsity. In the field of model merging, we may want to merge some models created from different analyzations or different tasks. So we're going to cluster 2 times n channels into n. So this is merging. And let's see the results. The left table shows the model merging on different tasks. Right table shows the model merging on different relations. We compare the model folding with some state-of-art model merging methods. WM is the weight matching. Zip8, yeah, is also a state-of-art method. On 2 models, WG11, ResNet18, played on different tasks. One is, for example, CIFAR10 with the labels of 0 to 4, and other task is label from 5 to 9. And we merge these 2 models to see if we can get better results. And interestingly, the model can give you better performance than the weight matching and the plate, both in WG11 and ResNet18. And if you treat model with different analyzation, if you want to merge them to have better performance, yeah, we can also see better performance if you use model folding. Yeah, you see this is, for example, 92 can defeat the debates 87 or with matchings 89. Interesting. Okay, that's the performance of model merging by extend model folding to this domain. If you go back to very beginning, as I mentioned, we are going to compress models into small size and can fit into edge devices. Let's see some real scenario use cases. We just integrate model folding into the standard deployment pipeline for edge deployment. For example, in JSON, ESPI, or Arduino Nano 33 Bluetooth. 10% sparsity they work. Yeah, because you can find 10% redundancy easily, but for high sparsity, the model folding can give you 2.5 times faster and 1.8 times less RAM usage without data without fine-tuning, but keep a good accuracy here. So that's good. I already show you some interesting results in the computer vision and edge deployment IoT scenarios. And someone may say, dude, you're just showing some results for ResNet18. Where's the LLaMA? Nowadays people are talking about large language model. Yeah, we did some results in the large language model, especially for LLaMA-7B, without any data usage or fine-tuning. So here we take the LLaMA, I think it is version 1, yeah. LLaMA 1/7 an example, and we evaluate at 20% sparsity compared to some state-of-art structure pruning method for LLaMA, and we evaluate on the perplexity on weak test 2 data set. Smaller value means better, and other tasks. So for example, the easy solution is magnitude pruning 20% sparse. You delete the most 20% less useless neurons, you get, wow, this is super terrible. And if you look at other methods, for example, LLaMA pruner, you need to do gradient descent, or you need to compute the gradients, which is not good. Or you can also do flap, one select GPL should you get some lower value, but you need a small site of calibration data set. And you need to be careful for the calibration data set choice. You need to correct the one and run it, run the pruning method on it. But here, with model folding, in order to achieve 20% sparsity, you do not need the data. You do not fine-tuning, you get 13.33 perplexity on big test 2. And also close performance to other methods in different language tasks. Yeah. Okay, so short summary. I guess you guys have many questions, so I will give you a short summary here. The model folding, as we propose, is total data-free, fine-tuning-free model comparison method by 2 data-free version repels to correct the batch normalization layers for the air and for the air. But for LLaMA-like models, there is no bin layers. You do not need to run repel here, and you cannot run it here easily. And I will propose the model folding and defeat or be close or surpasses performance of state-of-art data-free model comparison methods like the IFM in the computer vision tasks or the short GPT in the large language model domain. So there is this QR code. You may want to scan the QR code to get access to the project website, including some results, a link to the paper, or the source code. Yeah, thank you so much. That's my presentation today.